What is up, good people? This is section 2.5, day number 2, solving systems of equations, and today we're going to use the technique of elimination. So that makes 3 total techniques. The first day was graphing, last video was substitution, and this video is going to be elimination. Here's the first big idea from today. Not only can you multiply all the terms on both sides by a number, you can also add those equations together. This helps eliminate a variable. So just mathematically what I'm talking about, you could have 2 separate equations that are true. Like we know that 1 plus 2 is 3 and 2 plus 3 is 5. But if you add these 2 different equations vertically, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, you can actually add 2 true equations together to get a third true equation. How cool is that? We think we've seen that a little bit before in this class. But every time we use an elimination technique, we're gonna use this fun fact. Let me show you what that looks like. So let's start off over here with example 1. We got the red equation, we got the blue equation. Now if you add them together, all of a sudden 5x plus negative 5x eliminate each other. They're canceled. I'm not even going to write 0x. I'm just going to leave it blank because it's less handwriting and it's fine. And then 4y plus negative 1y is 3y. 10 plus negative 25 is negative 15. All of a sudden, we've come up with a third equation that also must be true. And because there's only one variable here, the other one got eliminated, we can solve this. Yay! We can figure out what y is. It's y equals negative 5. Awesome. Let's take that info and put that back into one of the other equations. Doesn't matter which one. I'm going to choose the red one because there's fewer negatives. 5x plus 4 times negative 5 is equal to 10. You do the multiplication, and then undo the subtraction, undo the multiplication, you get x is equal to 6. And so now I know what x is, I know what y is, I'm going to list them out here as an ordered pair. That's actually way faster. This particular problem is way faster to solve than substitution. And also kind of, I think, from the studentship point of view, more likely to get it right if you're going to use a technique like elimination right here. Just because there's less, you don't have to distribute like we did before. So elimination is a really great technique to use, especially when it looks like this, especially when you got both equations in standard form, and then all of a sudden you can, boom, just add, you can recognize, oh, 5x and negative 5x, elimination, because you just add them and all of a sudden they eliminate right there. But if you're required to use elimination and you don't have such easy to eliminate variables, there's a preliminary step you might have to do. Notice the red and the blue equations here in example 2, you don't exactly, if you tried to add them here to eliminate a variable, they wouldn't eliminate. 4x plus 2x is not 0x. Negative 2y plus y is not 0y. So if you try and eliminate it right off the bat here, it's not going to work. You're just going to get a third equation with two unknowns and with 2 unknowns, which you can't solve. And to find out, as a number, like you could here. So you got to do a preliminary step. You got to think to yourself, self. So what number could I multiply the entire equation, all the terms on both sides, by in order to produce equations that do eliminate? Check this out, negative 2, because I'm choosing the x. If I want to eliminate the x's, I really wish this were a negative 4, and I can arrange that by multiplying the entire equation by negative 2. 2x times negative 2 is negative 4x. Negative 2 times y is negative 2y. Negative 2 times 6 is negative 12. And all of a sudden, when I add these 2 equations with a new version of the blue equation here, all of a sudden, the x's eliminate. Perfect. It really comes down to finding this choice right here, like choosing, having foresight to know, negative 2. Once you do that, then you can add them. 4x plus negative 4x is nothing. You don't have to write it. You don't have to write 0x. You just boom right there. Negative 2y plus negative 2y is negative 4y. And 4 plus negative 12 is negative 8. Solve it. You get y equals 2. Yay. Take that y equals 2, put it back into either one of the equations, the red or the blue. Doesn't matter. I'm going to choose red just because it's on the top. I don't know. I probably could have chosen the blue because no one likes subtraction more than addition. But anyway, it doesn't matter. 4x minus 2 times what y is, that's the value of y, we know it's 2, is equal to 4. So if we know the value of y, we can find the value of x. Do the multiplication, undo the subtraction, undo the multiplication, and do x is equal to 2. So I'm going to list it out. If x is equal to 2, y is equal to 2, you can often just present your solution as this, 2 comma 2. That's what x and y are equal to. That's awesome. So let's go here. Example number 3. All right, if we just try and eliminate these right off the bat, we're just going to get, like, if we add these equations together, we're just going to get 6x and 8y, and that's not going to help anything. A third equation with 2 unknowns in it, you just can't solve. But I have the foresight to know that I can take, if I try and eliminate the x's, I would really need 4x and negative 4x, and I can arrange that by multiplying the red equation by negative 2 as a preliminary step. Everyone say preliminary step. Yeah, those preliminary steps are going to make it all work, make it all happen. So then the 2x becomes negative 4x, the 5y becomes a negative 10y, and the 24 becomes a negative 48. Now, if we add the equations together, we can, the x's eliminate. We get nothing. And negative 4x plus 4x is nothing, 0x, and you don't even have to write it. Negative 10y plus 3y is negative 7y. Negative 48 plus 20 is equal to negative 28, and y is equal to 4. So then take what y is equal to and put it into one of the other equations. Doesn't matter which one, red or blue. I'm just on a roll at this point. Might as well do the red. I probably should have done the blue just to switch it up and demonstrate to you that it doesn't matter which one, but it really doesn't. 2x plus 5 times what y is. I mean, now we know that the value of y is 4. It's equal to 24. Multiply 5 times 4, undo the addition, undo the multiplication. You get x is equal to 2. Therefore, you can present the solution as 2 comma 4. Awesome. All right, preliminary step. This you only had to multiply the red equation by negative 2. Sometimes, and that's because like 2 is a factor of 4. Right? And I readily knew that 2 times negative 2 gave you the opposite of positive 4x. But sometimes you don't have those kinds of things here that are easier to look at. What you got to do is you got to multiply both the red and the blue equation by this, to get the least common multiple. The least common multiple of 2 and 4 is 4. The least common multiple of 2 and 5 is going to be... Oh, no. Oh, I'm sorry. I'm looking at the x's. I thought what I'd do is switch it up and do the y's instead. So I'm going to eliminate... You notice down here the y's disappear. So the least common multiple of 7 and 3 is going to be 21. And one of them is going to be positive and the other one's going to be negative. It doesn't matter which one's negative. It doesn't matter which one's positive. Like, I could have just as equally done negative 3 and positive 7 to get one positive 21 and one negative 21. Why? And just like the others, I could have just as equally chosen negative 5 and positive 2 to get, a positive 10x and a negative 10x, and they would eliminate. But I'm just going to eliminate the y's right here. And so you can see that's 3 times 2x is 6x. 3 times 7y is 21y. 3 times 17 is 51. Then that's how you get a new version of the red equation with a least common multiple of 21 here. And then negative 7 times 5x is negative 35x. Negative 7 times 3y is negative 21y. Negative 7 times negative 1 is positive 7. And so now when we add these two equations together, we do get elimination. The y's, positive 21y and negative 21y, they cancel out. There's nothing there. You don't have to write a term. 6x plus negative 35x is negative 29x, and 51 plus positive 7 is 58. Dividing both sides by negative 29, you get x is equal to negative 2. And again, studentship tip, both your textbook and Alex just randomly generate equations that happen to have usually whole number or integer answers. So if you get a decimal as an answer, then you better check your work. Fun fact. All right, check this out. And now that we know what x is equal to, we're going to write the blue equation again. You could have written the red equation. You could have written any version of these equations and it would have worked. I'm just going to choose the original form of the blue equation because I'm playing favorites. Blue equation, you're my favorite. 5 times negative 2 is negative 10 plus 3y is equal to negative 1. Undo the addition, undo the multiplication. You get y is equal to 3. And you can present your solution like this, instead of parentheses, x value comma y value. And I want you to figure out what goes underneath this red dot and save it for the save it for the Edpuzzle question at the end. All right. Let's see. Here's the big idea number 2. Big idea number 1 was that you can multiply all the terms on both sides to add equations, and this helps eliminate a variable. Big idea number 2, doesn't matter which method you choose, all 3 methods produce the same solution set. So let's do this. Let's take this system of equation and solve it 3 ways. Taught you graphing, taught you substitution, and today I taught you elimination. Let's do it 3 times and just verify this big idea. So you can see graphing. Boom, y equals 3x plus 2, y equals 2x. You notice we had to rearrange this. I had to add 2x to both sides. But once I do that, it's a lot easier to go equation table graph twice to produce 2 different lines, and there's the intersection, -2, -4. And that's the answer, -2, -4. If you wanted to use substitution, this is here's a go y already by itself, and so you don't have to do any further rearranging. You just rewrite the second equation as, instead of writing a y, you write what y is equal to, and it's equal to 3x plus 2, inside a set of parentheses. But then you combine the like terms, you get x plus 2, solving for x, you get -2. Take that and put it back into one of the original equations, like the top one, and then you get y is equal to 3 times what x is equal to. It's equal to -2, plus 2, and you get y is equal to -4. Present your solution. It's the same. Big surprise. Elimination. Here's another thing you got to do for elimination. If you are required to take to solve a system of equation using elimination and they're not already in like standard form, you got to put them in standard form. You got to line up all those x's on top of each other and all the y's on top of each other and the numbers on top of each other so that you can add them. It's a nightmare to do it if you don't. So although the bottom equation is in standard form, we should probably subtract 3x from both sides over here to get -3x plus y is equal to 2, -2x plus y is equal to 0. Now, if you try and add those at this moment, nothing's going to eliminate. You don't have a positive and negative version of the same term. So I think I'll multiply the top equation by -1. All of a sudden, we get positive 3x. Like -3x times -1 is positive 3x. Positive y times -1 is negative y. Positive 2 times -1 is -2. And now when we add, we can eliminate the y's. I chose that because I chose to eliminate the y's because I thought finding the least common multiples of 3 and 2 would require like two different numbers. You have to multiply the top and the bottom equation. But here you can just multiply, if it's already y and y, you can just make one of them negative. And so we've got, when you add the two of these equations together, 3x plus -2x is just 1x, and I'm just writing x. The y's eliminate, you don't have to write them. -2 plus 0 is -2, and that's how you get x. Substitute -2 back into one of the original equations. I think I'm going to choose this top one right here because it's already, y is already, all by itself. Although you could have done the bottom one, doesn't matter. You get y is equal to 3 times what x is equal to, -2 plus 2. Solving for y equals -4. Boom, -2, -4 is the solution. Again, big surprise. The big idea is that it doesn't matter which one you use. All 3 methods produce the same solution set. And if the instructions don't necessarily necessitate or require a particular method, then you can choose whichever one you want, based on looking at the equations and seeing which one might be most convenient for you. Honor students got to be flexible. You got to be able to do all 3 in any given situation. Big idea number 3, regardless of the method, it doesn't matter which choice you make, graphing or substitution or elimination, you can identify these 3 different cases. And here are the 3 cases. Let me show you what this looks like. We've got 3 different sets of systems of equations to look at. And so here's the first one. Here's the first case. If you solve it by graphing, you can graph this one and this one, go equation table graph twice, and find the intersection. It has, how many solutions does it have? It's got 1. You can solve this one by graphing. Again, go equation table graph and find you've got railroad tracks. These are parallel lines that will never intersect. You might be able to guess that because you can see all the coefficients here are the same. 1, 1, 1, 1. And so you're producing parallel lines. They're going to have the same slope. So there are no solutions to this case. One solution here because there's one intersection. Zero solutions here because there's zero intersections. And here, there's a third different case whereby you just actually look at these, and if you multiply the top equation by 2, you can get the bottom equation. It's the same equation. You go equation table graph twice, and you produce the same exact points. You plot these two lines on top of each other. They coincide completely along the graph. So where are the intersections? There's an infinite number of intersections. There's just so many intersections going on. Every single point on the line is an intersection. So there's also, if there's an infinite number of intersections, there's also an infinite number of solutions. That's what the three different cases are going to look like when you graph. One solution, no solutions, infinite number of solutions. What's it going to look like when you solve by elimination? All right, well, here's the same equations if you, or substitution. If you add these two together, noticing we got a positive y and a negative y, ooh, perfect candidate for elimination. Add the two together, x plus x is 2x. Positive y plus negative y eliminates. You don't even have to write it. 2 plus 0 is 2. So you get x is equal to 1, and then take that and put it back in the original. What it looks like when you use elimination is you get the solution. You get an answer. You get 1, 1, solution. Yay. However, when you try and do the same thing here, using either elimination or substitution, you get, let's see, you realize you can add these two together. You get positive x plus negative x is 0x. Positive y plus negative y also eliminates. You get both variables eliminate. Hold up the phone. Something is really weird. So all of these added together gives you 0, and 3 plus 1 is equal to 4. You get something like 0 equals 4. That is a false statement. Both variables drop out, and you get a false statement. Then you know that there are no solutions. That's your indicator. No solutions. Let's take a look at this. Negative 2x plus 2y, and then positive 2x plus negative 2y. When you add these together, also all these variables drop out. There's no more x's or y's. They're all gone. You're just left with negative 8 plus 8 is 0. 0 on this side, 0 on this side. That's actually a true statement. No variables with a true statement means it doesn't matter what value you choose for x. You can calculate a value for y to be a solution. So there's an infinite number of solutions. Sometimes a vocabulary word thrown around is that it's an identity. All right, but we also remember the vocabulary from last time. Consistent, like this, if you have one solution, that means it's consistent. And even if you have an infinite number of solutions, that's consistent. Because the question is, does it have at least one solution in the solution set? And if the answer is yes, then you can call it consistent. That's why this is inconsistent, because there are no solutions. You can't. That's the false statement indicates that there's no intersections on the graph, no solutions for the system. So we call that inconsistent. And the second question is, did we, in order to come up with a solution set, did we need both equations to do it? And yes, you need both equations to do it. We call that independent. Here, we needed both equations to come up with a solution set, so we call that independent. And here, the solution set can be derived from only one equation. You only need one equation to do this because the second equation is just a duplicate of the other. So we call that the opposite of independent, which is dependent. Boom. There's your math. I wanted to say that my favorite movies of all times are the original Lord of the Rings. It came out in the early 2000s by director Peter Jackson. Brilliant movies, tons of Academy Awards. Come at me with your favorite movie because mine's better. See you in class.